and start broadcast.
The broadcast is now starting. All attendees are in listen-only mode.
Good morning to you. This is Mark Richardson speaking from Vibrant Technology in Northern California. I apologize, we're a little bit late here this morning, but we will spend a good hour together, so thank you very much for hanging in there. Those of you that are still online listening to this broadcast, I have Brian Schwarz in the room with me. He's going to be the technical director, and we're going to do this broadcast. We're using GoToMeeting, and so we're using the GoToMeeting webinar software here. We always have a few little technical difficulties with it. The animation doesn't work real well on my computer, so we were fussing around with that, trying to make it better, but we'll just have to live with whatever shows up here on the screen. Today's topic is OMA curve fitting, or operational modal analysis, and the topic is how do we get modal parameters, mode shapes, frequency, and damping from data that is not taken in a specific manner that is normally used for modal analysis, and that is that we measure frequency response functions, or FRFs. An FRF is defined as the response, which could be displacement velocity or acceleration, divided by the excitation force that caused that response. And we can do that with multiple forces or with a single force. Now, the most common way of taking data is with an impact hammer and an accelerometer. There we measure the acceleration response divided by the impact force. And that type of a measurement, the FRF, isolates the modes of vibration in that data. It's a frequency response function. It's a frequency spectrum, and the peaks in that spectrum are evidence of modes of vibration. So that's a normal way we do modal. But if we have an operating machine, or if we're testing a bridge or a building, something like that, we cannot measure the forces. The forces are distributed, they're internal, they're created, maybe they're acoustic, maybe they're the wind blowing on it, the traffic, whatever it is. We cannot measure the forces. So all we can do is measure response, and typically that's done with accelerometers. And then we can form, in order to get shapes, mode shapes, or ODSs, operating deflection shape, which is similar but different, we need a phase relationship between each of the responses. Now, an autospectrum, which is a spectrum of a signal, will certainly show us peaks in the spectrum. Those may or may not be due to resonances, because we're just measuring response, and we're not dividing out the spectrum of the force as an FRF does. So if we're only measuring responses and we have peaks in the data, we can go ahead and curve fit those peaks and attempt to recover the operational modal, or what are called operating mode shapes. They may or may not be mode shapes. This is where the animated picture comes in, where we can look at the shape in animation and determine whether it's simply what's called order related. The machine is simply unbalanced, or it's running and there's some unbalanced forces that are pushing the machine around. And so the ODS that we look at, or even the curve fit result, what we might call an operating mode shape, may be a combination of the resonance and also just the forced response of the structure. So we have to be a little bit careful with OMA data. I'm going to take you through an example here today where we're going to form cross-spectrum measurements between a number of accelerations and a reference accelerometer. Now, a reference is a fixed accelerometer location. And the reason we need a reference is so that we can get the phase between that accelerometer and any number of what we call roving accelerometers. Now, the roving can be all taken at one time if I have a multi-channel analyzer or data acquisition system and I can acquire all that data at one time, or if I only have, let's say, a two-channel analyzer or data acquisition system or a data collector, a portable data collector, then I need to measure the reference at all times when I measure one or more of the roving accelerometers. Then we can bring that data into, we can actually bring it into EmiScope and form a cross-spectrum measurement between the reference and each of the roving accelerometer locations. That gives us a phase. A cross-spectrum has not only magnitude in it, which would have some peaks, either due to resonance or just order-related peaks, or 60 cycle or other things can be in there as well. Whatever is in our response, we're going to see some peaks in that data, but we're also going to have the phase of that roving response relative to the reference. Now, if we collect a whole set of data like that, then in fact what we've got is the phase of each of the roving responses relative to each other. Since they're all relative to the reference, they're also relative to each other. And that's sufficient to get a mode shape or an ODS, which is really what we look at when we animate data directly from these a set of, let's say, cross-spectrum measurements. Now, in EmiScope, we have another type of measurement called an ODS-FRF. And we use that primarily for animation. And that's a hybrid measurement where we take the autospectrum of each roving response and we combine that with the phase of the cross-spectrum between that roving response and the reference. So we take the phase off the cross-spectrum, we take the autospectrum, and we marry them together in something we call an ODS-FRF. Now, those measurements are a little different than the cross-spectrum directly. Either one of those types of measurements can be curve fit to recover what we call the operating mode shapes. Now, there's one more step involved here, and that is that we use an FRF-based curve fitting algorithm. All of our curve fitters are based, or let's say presume or assume that our measurements have the form of an FRF. Now, in the case of an OMA situation, we don't have FRFs. We have cross spectra or we have ODS FRFs. So the first step we have to go through is to process that set of measurements with a special windowing. And the best way to illustrate that is to actually go through and look at some data here. So let's go ahead and do that. I'm going to open up one of our tutorial projects in EmiScope. Now, I'm going to say some things here, but I'm going to skip through a lot of steps. So I'm assuming that if you're listening here today, let me put this away, Brian.
Okay, hit the orange button.
Yeah, okay. So you should be able to see my screen here. This is EmiScope on the screen, filling the screen. I've got the start page up here. It's showing my recent projects, some things that I was working on that I recently saved, the last 5 things. These are my VTPRJ projects. I can open any new project. I can create a new project. And remember that a project is a collection of other data files, and it's all stored together on the disk. into a VTPRJ file. That's a Microsoft SQL file. But we have structures, data blocks, shape tables, acquisition windows, reports, programs, and added files, which are typically our movie files. So these are all the different things that can go into a Emiscope project. Along my tab line up here, you can see the first tab is always my current project. There's nothing open here, so under these different categories there are no files yet because I haven't opened a project. Now I can go to my demos tab. Your software should have some demos, and if I just move the mouse on top of the demos, typically it will tell me something about them. In this case, I'm not seeing anything. Let's just go to a different one here. Okay, well, I want to go over here to one called tutorials, and I'm going to click on this guy right here. Okay, now I can see what's in there. This is tutorial number 9. This is out of the operating manual. Our operating manual and our help file is divided into 2 halves. Let me show you that real quickly so that you can do this when you're on your own. That's the best way to learn some of these things. Just go back and do it yourself. So here's the tutorial help and here's the command help. If I open the tutorial help, and let me make this large, we'll just take a quick look at this. Down here there are 15 different tutorials. So let me expand this a little bit so we can see some of this. And number 9 in here is called Operational Modal Analysis, or OMA. So you can click into that chapter in the manual and the help. Remember that the help and the manual are identical. We actually build the manual from the help and then create a PDF, which is also stored on your disk. So you can go and read the PDF copy of the help in a manual, in a page format. Here, if I click through, you can see some different topics here. We're going to do a simulation, and then we're going to acquire some cross spectra. Then we're going to curve fit the cross spectra. Then we're going to compare some mode shapes. So this simulation is actually going to use a feature in our acquisition window called simulation, where I can take a set of mode shapes and from those synthesize some FRFs, excite them with some this FRF model, which we call a MIMO model, multiple input, multiple output model, with some random excitation. From that, we're going to measure the cross spectra between a reference and a number of roving accelerometer locations, and then we're going to curve fit those cross spectra. So we'll get down to doing the curve fitting here, which is the topic that we're covering here today. But you can see there's a number of other steps involved before we can actually use the curve fitter. And as I said, we're going to use FRF-based curve fitting on these cross spectra to recover the modal properties of this structure. And we're going to use the Jim Beam structure here. So this is kind of a summary of what we're going to do today. Okay, in the last slide here, let me just go through the summary and we'll come back to this. I'll make this a little larger. I'm going to push the control key and spin the mouse wheel, and you can see that that makes the text a little larger, so I can actually see what it's saying in here. Okay, so we're going to start out with a modal model of the Jim Beam. Jim Beam you're familiar with if you used Emiscope. We use that as one of our demos, and we can do curve fitting and MIMO and a lot of other things with the Jim Beam project. So we're going to use what's called a MIMO simulator, and that's part of an acquisition window. If you have that option in your Emiscope, then you can do that. You can also do this in a data block window, so you can do this simulation either with or without the acquisition. We're going to use acquisition here today and simulate acquiring the data from the real Jim Beam structure, if you will. Okay, so we're going to simulate the acceleration response of the beam due to burst random excitation. So we're going to put in some burst random excitation, and the reason we use burst random, I won't go into the details, but that is an ideal excitation signal for doing modal work when we use a shaker, one or more shakers. This was developed back in the 70s for testing the Boeing 747 at Boeing, and we've been using it ever since. It's the best signal there is for doing modal work on, let's say, a nonlinear structure. The random excitation combined with spectrum averaging will remove the effects of any nonlinearities in the structure, and certainly something like a 747 we would assume is nonlinear. Modes are only defined for linear dynamics, so we want to average away the nonlinear effects and end up with some measurements which show us the linear motion of the structure so that we can curve fit those measurements and get some mode shapes. So that's the whole idea behind burst random. So we're going to excite the structure at a DOF here, which is 0.5 in the z direction. So that we'll see that in a minute. That's out on the beam at one of the on the top plate in one of the corners. That's a lively place to excite the structure. So we're going to put some random force into the modal model, which is our dynamic model for the structure, at 5 in the z. We're going to measure 99 channels of acceleration response using the MIMO simulator. So we have mode shapes from Jim Beam with 99 degrees of freedom in them, 33 points, X, Y, and Z motion, 3D motion at 33 points. That is the 99 roving channels of accelerometers, or let's say the 99 channels of roving accelerometers that we can get mode shapes from. With that data, we're going to measure 99 or calculate 99 cross spectra, and that's done in our acquisition window. So Emiscope has some of the functions of an FFT analyzer built into it. The acquisition window in this case is going to calculate cross-spectrum data, 99 cross-spectra from the time records of the acceleration responses coming from the MIMO simulation of the Jim Beam. So this is simulating a situation where we would actually be testing a structure with 99 accelerometers on it. Now, one of those accelerometers is going to be the reference, and that is going to be, in this case, we're going to choose the reference to be 0.15 in the z direction. So the next line here shows that we're going to form cross spectra between the 99 accelerometers and the, okay, Brian, this popped up on me here.
Just hit the X at the top corner.
All right.
Or, no, not that X. Hit the orange button on the left to close it again.
Okay. There we go. All right, so 15Z is going to be our reference. 5Z is where we're putting in the force. So we just kind of mix things up here a little bit. We could pick any accelerometer for a reference. In this case, we're going to pick a different one than where the force is being applied. Now here's a step I mentioned to you earlier, the deconvolution window. This window essentially clears out the second half of the correlation function, which is the inverse Fourier transform of the cross spectrum. So what we do in Emiscope is we inverse Fourier transform the cross spectra, the 99 of them. We clear out the second half of the trace. for all 99 traces. And the reason we're doing that is that that portion of the correlation function is due to the reference, and we don't really care about the reference. In order to get mode shapes, we care about the roving portion of the signal. So the correlation function has what looks like two impulse responses summed together in it. One that's the decaying impulse response of the roving accelerometer, and then a kind of an inverse of the decaying response or a growing response of the reference accelerometer. So we're going to remove that data, then Fourier transform back to the frequency domain and use an FRF-based curve fitter to recover the modal properties. So that's what we do. Now, other people use an exponential window, or they may use a rectangular window to simply clear out the second half of the data block, or to minimize the second half of the correlation function. Those all work as well. We use something at Vibrant called a deconvolution window, which is a smoothly transitioning window from 1 to 0, and it clears out the second half. So we have a tech paper about that. If you go to our website and look up deconvolution window or OMA curve fitting, there's a paper out there that will explain some of the details. Then we're going to use a stability diagram, which is a curve fitting method, and there are some curve fitters associated with that, and we're going to recover the poles, or the frequency and damping of the modes, and then we're going to get the mode shapes and compare those with the original the mode shapes of the original modal model that we used to start this whole simulation. So it's kind of a round-trip simulation. We start with a set of mode shapes, we simulate random response, we compute cross spectra, we curve fit them, and we'll recover some mode shapes and compare those with the original. So that's the idea here. Let's go ahead and start some of that right now. I'm going to close this. I'm going to go back here and open up from my tutorials folder, tutorial number 9. Again, it's just Jim Beam. So let me open that up. And it's a slightly different project because it's got some mode shapes in it already. And you can see there's actually a program running in here that does all of these steps automatically. Now this is another option in EmiScope. I'm going to say no, cancel that right now. Here is a program in EmiScope that if I tell it to run, it will do all the steps for me in an automatic fashion. So this is a new option to EmiScope. Well, it's not real new. We've had it out for several years now. The idea here is that every command in EmiScope can be put into a spreadsheet like this. And you can see that we just simply specify the window that we want to execute the command in, and the command in that window. And here's a little description over here. And if there's any parameters on the command, they show up down here under the parameter spreadsheet. So this is a new kind of a feature in EmiScope that we could use to go through this simulation very quickly. But we're going to do it by hand here. We're not going to use the programming. So I am going to, first of all, let's just start the animation. I'm going to come up here and let's, so here I have a set of mode shapes. Down here I already have some results, OMA mode shapes. Let's just close that. And let's just animate these mode shapes. Again, you can do this on your system. And so I'm going to go here and start the animation, and we'll look at these mode shapes. So this is data that we've had around for many years. You can see this is the first mode of the structure. Now, it's actually sweeping. I've got it on sweep. How do I know that? Well, it already jumped to the second one. See, it's sweeping through the mode shape. So sweep animation will either sweep through my time or frequency data if I'm animating from a data block, or in this case, I'm sweeping through the shape table. And so I'll just leave it sitting there. This is a good way to make a movie when you're all done. You can put it on sweep, and the sweep animation, if your animation source is a shape table, in this case it is, then you could just start the movie and sweep through and animate each of the shapes in your shape table and make a movie of them all automatically. So you can just let it run through the cycle. Now there's one other thing going on here. If I right click over here, it's completing so many sinusoidal cycles of each shape, and it looks like it's about 3 or 4, and then it goes to the next one. Well, where was that set up? That was set up in the shape table options. So if I go in here and then I go under animation, here is sweep animation, sine dwell cycles per shape, and it says 4. So what I'm seeing here is that it's going to do 4 cycles per shape as it sweeps through my shape table and shows me the different shapes. So there, when I close the window, it stopped the animation. I'd have to start it again. Now, I can start it either from the shape table itself. If I go under Animate, Animate Shapes, it will start there, or I can start it under in the structure window. So there's my modal model. Now, what do we mean by modal model? Well, these shapes have been scaled in a certain way, and again, the data would have to be calibrated. You'd have to put in the calibration factors for your accelerometers and the units and so forth, if it's an accelerometer in G's, and put in the sensitivities or the cal factors, so that when you curve fit this data, you're going to get data that's scaled correctly. Now you can see down here, let me make this a little larger. I'm going to click on this spreadsheet and hold down the control key and spin the mouse wheel. So that makes it a little bit easier to see. You can do this on any spreadsheet. Hold the control key, spin the mouse wheel after you've clicked in the spreadsheet, and it will become larger so you can see it. And here you can see that these shapes have been scaled to unit modal mass. The measurement type is UMM mode shape. Unit modal mass, you can see they have units in them. Now mode shapes are eigenvectors. They normally don't have units, but these mode shapes have been scaled so that they carry units with them, and the units are inches per pound second. That's a little strange. Of course, those are English units, so I apologize. We Americans are the only ones left on the planet who use the imperial units. Inches and pounds, so you would normally use centimeters, millimeters per Newton, and then you got seconds in there. Well, that's because these mode shapes came from what we call residues, which are the numerators of the FRF. Remember, we're doing FRF curve fitting, and the numerator of an FRF has units of, normally it would be G's per pound second, because remember the denominator has frequency in it, either the modal frequency and or the modal damping, and they have units of radians per second. So that's where the seconds come from. Those radians per second cancel with the radians per second in the numerator, and then we get the units of the FRF, which would normally be G's per pound. Now this data has been integrated. So you can see that we went from G's down to displacement or inches. Normally a modal model will be like this, and the units of a modal model, if you get it from an FEA model, would be the same. It would be in displacement per unit force times seconds. Okay, so now we're going to go and open up the acquisition window. Now you can see my project here has a structure model. It has some data blocks in it. Here's a data block. Here is an acquisition window, and then a number of programs which we looked at earlier for doing this whole process automatically. I'm going to open up the OMA acquisition window. Okay, now it's saying shapes are selected in the following shape table. Shape mode shapes, SHP mode shapes. That's the one I was just animating out of. So remember, the rule in Emiscope is if things are selected, we only operate on the selected things. If nothing is selected, we operate on everything. In this case, we want to use all of the mode shapes, so I'm going to unselect the shapes in the shape table. And now I have, let me right-click here and make this large. Here is my acquisition window. You can see it's already got some data in here. And I need to set this up. It's probably already been set up because it was used previously. Let's just go through and see how we set this up. Now remember, this is going to use the modal model, or the mode shapes. The measurement we're going to make is across spectrum. We're going to do 50 averages because this is fairly noisy measurement. Why is it noisy? Well, we're exciting with random noise. That's why. Sampling, we're going to collect 2,000 samples, and the sampling rate is, well, my span here is 2 kilohertz, 2,000 hertz. So I'm going to have what? In the frequency domain, my resolution, I'm going to have 2 hertz between samples. So you can see there's just two numbers in here that I need to specify. The number of samples and the span, which is half of the sampling rate. So the data is actually being sampled at 4,000 RPM, 4,000 hertz, but we can only look at half of that in the spectrum. So you can see down below here we've got a spectrum, cross spectrum. So the time records are up in the top. The frequency records across spectrum are in the bottom. We got 2 trace displays here in this window. The source, now this is where we're going to excite with burst random. The burst width is 60% of the time trace block. So let me see if I can see that here. I'm not seeing it. It's turned off. But these are all the responses of the accelerometers that I'm scrolling through here, up to 33Z. So there's 99 of them in there, and you can see the effect of shutting off the random response, or the random excitation. The response, which is also random for each of the 99 accelerometers, then decays down because the force has been turned off, the shaker's been turned off, and it decays down to 0. So these measurements, the reason this is done this way is that these measurements are completely contained within the sampling window or the acquisition window. Therefore, we don't need to use a Henning window. There's no leakage. They are as clean and as complete as we can get by doing it this way, using a burst random. Down below here is my channel spreadsheet that's basically telling me about the measurements that I'm making. You can see that I'm actually acquiring 100 measurements, except I've turned off channel 100 here, which is the, let me just turn that on right now, and I'll turn on the acquisition. Up here there's a command called front end scope. So I'm going to turn that on and just show you what this data looks like. Now this data is coming out of the simulator. I'm in the scope mode. So this is just like an oscilloscope here that's running and acquiring 2,000 samples of data. Now if I go all the way down here to the bottom, there is the burst random. There's the burst random force that I've acquired from this simulator. That's channel 100. And then in front of that are the 99 channels of random response. So again, if I was doing an OMA, could I do it this way? Not really, because as I said earlier, the OMA, I can't measure the force. I would just get random response. So if it was random excitation, like the traffic on a bridge, or a car driving around a racetrack. Then I'd have to use a Hanning window. You can see over here in the channel spreadsheet, there's no window being applied. Window type, well, there is. It's the rectangular window. I can apply a Hanning, a flat top, a force, an exponential. These are different windows I can apply to my data. In this case, I'm using a rectangular window, which means just take the data the way it is. Don't do anything to it. If I were to apply a Hanning window, that would reduce the amount of leakage due to these random signals. In this case, I don't need to do that. In the real world, if I had 99 accelerometers out there on a structure, I would need to use the Hanning window to make these measurements. Okay, let's go ahead. I'm going to turn the channel 100 off again because we're not going to use that. We're going to use channel, let's go up here and see. I'm going to tell the acquisition window to calculate, let me see, 5Z. We don't have this set as both. My input channel, I want to set this one to both. I want that to be both my reference and my response. So what I'm going to calculate here is, here we got 15Z. Oh yeah, 5Z is, I got it right now. 5Z is where we're putting in the force. 15Z we're going to use as a reference. So you see 15Z down here. Let me make this spreadsheet a little larger so you can see that. And I'm going to make this, we'll scroll down here. You can see that 15Z is actually channel 45 in my acquisition front end. That's going to be both an input and an output to the MIMO model, which means it's going to be a reference as well as a roving. We use those terms interchangeably. Roving is typically the output and reference is the input, although there's a difference there. If I'm doing a roving impact test, then the roving would be my input and the reference would be my fixed accelerometer output. So different terminology there, but we're using, in the MIMO model here, we're using, when we say both, we're meaning that this is our reference. So I don't want two references. I'm just going to compute the cross spectra between 15Z and my 99 roving. So let's go ahead and do that. Now, rather than just run it into scope mode, I'm going to tell it to just start. Now, when I say start acquire, it's going to do 50 averages, the way I have it set up here, 50 averages of these cross spectra, and then it'll stop. So let me go ahead and do that. All right, saying, do you want to, with the simulator, do you want to add some more random noise? And I'll say no, I don't really want to add noise. But this is another way we can simulate noisy measurements and check out our curve fitting to see how well it does in the presence of noise. Obviously, all the curve fitters are designed to handle experimental noise because we get it in all of our measurements. So we can simulate it here and see how well the curve fitter does. Noise is not as bad as leakage or distortion or simply nonlinearities. All right, it's running now, so you can watch it run, and up here on the screen it's showing which average it's working on. It's up into the 30s already. So this is running very quickly, and you can see that as it runs, the averaging cleans up some of the noise on the measurements. So here are my measurements, and this is the log magnitude of the cross spectrum measurements. And they got noise on them, but that's okay. As I said, the curve fitter is not as sensitive to the noise because it's a least squared error curve fitter as it is to distortion or, let's say, nonlinearity in the measurements. That's much worse for curve fitting. So I'm done with that. Now I want to save these measurements, so I'm going to right-click here and under my tools, it says Save Traces. So I'm going to save these lower traces, and here is a data block with OMA cross spectra in it. I want to go ahead and save my data into that, and I'll just replace what's in there. Okay, so now I have a data block. Let me make this large. Notice I'm using this first command in the right-click menu, Center Data Block Window. That's a very handy command. Every window has that. If I put it back, let me put this down. The window goes back to a small one, but if I execute it, it goes back to a large one. So here I am in a data block with my 99 measurements. Cross spectra, you can see the units are G squared because essentially we multiplied the Fourier transform of the roving times the reference. Now let me show you what the inverse Fourier transform of these things looks like. Inverse Fourier transform. These are the cross correlations. And I mentioned to you that the first half of each of these measurements is like the impulse response. It really is the impulse response of the roving accelerometer. The second half of each measurement is sort of a reversed impulse response of the reference. So the deconvolution window that we're going to apply to this data will remove the effect of the reference, and we end up with something that looks like an impulse response of the roving. Now let me put this back, and we'll let the curve fitter do it automatically, and then we'll come back and look at the result here. So I'm going to put this back FFT. Remember, I can use the FFT all day long. It just converts the data from one format to the other, time to frequency, and then back again. If I go in to try to curve fit these, I get this message. Data block contains autospectra, cross spectra, or ODS FRFs. We talked about all those. We can curve fit these measurements and get modal parameters. These traces require deconvolution windowing before curve fitting them. Do you want to apply the deconvolution window now? And I'll say yes. Oh wow, internal error. Don't know where that came from, but we got a little issue here. But anyway, you can see that the window got applied, and it took out a lot of the noise. So that window actually removed a lot of the noise from these measurements. They're much cleaner now. Let me go out of the curve fitting, and let's go back and look at the inverse FFT. You see what happened? We removed the second half of the data in each of the traces. And what we end up with is an approximation of the impulse response. Now, it's not a true impulse response. Well, it is an impulse response, but it doesn't involve the force. It's strictly the response of each accelerometer. So let me go back to the frequency domain. And now let's go back into the curve fitting. Okay, so here we are in curve fitting, and this is the data block again, but above we have the 99 measurements, and below we have what we call a mode indicator curve. Now this curve is used to locate the resonance peaks in the data, and some of our curve fitters rely on that. All the curve fitters rely on telling them how many modes are in this set of data. Now we already know there's 10 modes in here because we got these responses from exciting the MIMO model that was synthesized from the modal model with 10 modes in it. So we know there's 10 in there, but let's see if the curve fitter can tell us that. Let me just compute one of these. Here's one called the CMIF. I'm going to go ahead and calculate it. Now it's trying to decide what part of the data to use, real, imaginary, or magnitude. in this case, since this is not true FRF data, the magnitude is the best choice. And there it is, and there's an indicator function that's got 5 peaks in it. Well, we know there's 10, and so this indicator is not going to allow us to use the quick fit to find all these modes, because it only sees 5 of them, and we know there's 10. So this is where the stability diagram really comes in, or is really useful, because what it's going to do is curve fit this data with a model size starting from one mode, go all the way up to a maximum model size of 50. And so it's going to lay all those pole locations, or the frequency and damping of the modes that it finds by curve fitting with one mode all the way up to 50 modes, and lay all that solution out so we can look at it, and then we can decide how many modes are in this set of data without having to count the peaks. So let's go ahead and do that. I'm going to just run this algorithm here. This is called the AF polynomial algorithm, and you can see that it's found a whole bunch of stuff here. Now the poles are colored. In this case, they're red and blue, and the reason that they have different colors is that all the poles that met these criteria here, the frequency tolerance had to be within 2 hertz, the damping tolerance had to be within 2 hertz, the number of poles, which we call stable, there had to be at least 5 of them that met the frequency and damping tolerance. Now remember, our resolution in our data was 2 hertz, so this defaults to the resolution of the data. And it's saying that if you can find a pole in this set of data, if you can find 2 poles that are within 2 hertz of each other, both frequency and damping values, and you can find 5 of them, then color them all the same color and draw them up. Now, let me zoom in here a little bit, and we'll take a look at some of the actual solutions. Let me zoom into these 2. And now you can see that the curve fitter has found a lot of estimates that are very similar. If I hold down the Alt key, I can actually look at the value of the frequency and damping. Now the damping is indicated by the horizontal line, and the frequency is indicated by the little vertical blip on each of the lines. So this is showing me the frequency and damping estimates that it got for these 2 poles, or these 2 modes. Now the pole is just the frequency and damping the mode. We don't have the mode shape yet, but we do have the frequency and the damping here. But you can see from this diagram that it's finding a whole bunch of stable groups, and each group is colored alternately either blue or red. Where do those colors come from? Let me just show you. We set that up here in the data block options again, and we use the contour colors. The first 2, because it's going to alternate between the first 2 contour colors. So you can see the red and blue here. If I wanted to use a different color besides red, let's just say I wanted one stable group to be orange and the other to be blue. Now you can see that my stable groups are orange and blue. So this is just a graphics tool to allow us to see stable groups. Now over here, you can see out here at some of the higher frequencies, there are some stable groups out here. They only have a few poles in them, but they met the criterion. The stable groups that I'm interested in are where the real modes are located. These other stable groups are what we call computational roots, or computational poles. So for instance, over here I've got one that's got 6 or 7 poles in there, that first group. I can get rid of that on my display by simply changing the number, the requirement of the minimum number of stable poles. So I will push that slider bar up, and you can see as I push it up, the picture keeps changing, and now I've only got stable poles. Well, I still got some out here that I don't think are, that I think are perhaps computational. So let me shove that there. I shove that slider bar a little bit higher. Now the picture has only got left in it the poles which are within 2 hertz of frequency and damping, and I've got to have at least 12 of them in order to call it a stable group. So now I can go ahead and save those groups, and what it's going to do is average together all the frequency and damping values that it found and put those into my my modal parameters spreadsheet over here. The other thing I can do is if I show all, you can see this filtering operation did quite a good job of getting rid of solutions that are meaningless. Here's what the curve fitter gave us. All of these different roots of the denominator. Remember, the frequency and damping are in the denominator of the FRF. So this curve fitting model we're using here is an FRF model with frequency and damping in the denominator, residue or strength of the pole in the numerator. The residues are going to end up being the mode-shaped components. So if I turn this back off to show all, now you can see what the filtering process did. So that cleaned up the solution so that we can get some usable results from this particular curve fitter. I'm going to go ahead and save those groups. So now I've got frequency, damping, and for this particular curve fitter, you can see it actually filled in the residues also. So it's got all of the information from one curve fit into my shape table, or not my shape table, but my modal parameters spreadsheet. And if I need to go over here to my residues, and now you can see that I can save these residues as a shape, actually with the frequency, damping, and the residues. Or in this case, I can actually look at the curve fit function that this data produces. So now I'm going to go through a synthesis operation. And it's saying, you know, you're going to use the AF poly method. Do you want to synthesize? And there is my curve fit function now, the red function, laying on top of, oh, well, I only got 9 modes here. So you see, I missed that. You can see that peak out there, that 10th mode out here. Let me stop it on a measurement. There's a mode out there that we missed because we pushed the tolerance too high in terms of the number of stable poles. So let me go back to the stability diagram, and I'm going to adjust this down a little bit, and bingo, there is that. You can see now I've got some estimates for that particular peak that I see in the data here, which is one of my modes out there. And I still got all the other stable ones in there. So I'm going to clear out my table here and put all new stuff in it. Let me scroll a little bit. Yeah, we could select the last mode. We could do that. Brian is kind of coaching me here and saying we could just save that one. Many times this is a good way to go. So I've already saved the other ones. Now the average results will be a little different because we got more poles in each of these stable groups, so they might average out a little bit differently. But the other thing I could do is simply I can do it in a couple of ways. I can turn on the band cursor, or I can simply display that area of my data and it will save what I'm looking at. Let's use the band cursor. That's a little safer.
Or you can use poles and surround the group, can't you?
Oh, Okay, Brian's coaching me here another way. Here I can save it, or I can hold down the control key. Now I don't know whether you can see that, but when I press the control key, you see that I get a little the mouse pointer changed, and now it's showing me a plus sign. If I drag and drop that plus sign, I can enclose any number of poles on the stability diagram that I want to, and it will average all those together and give me an estimate for that particular pole in my modal parameter spreadsheet. So let's do that. Remember, if I hold down the Alt key, it's going to show me the frequency and damping of the nearest pole. So here I'm just moving the cursor along with the Alt key held down, and it's showing me those values. But graphically, I can see that you know, this is a very stable pole. Let me scroll this up a little bit. If I want to just grab that group, I will hold down the control key, and I will now. Can you see that I've drawn a selection box around those poles, and now it's going to average those frequencies and damping together when I let go of the mouse, and you can see that it put the average value for that particular mode into my spreadsheet. So that's one way to do it. Now the other way I can do it, because I have the band cursor on, is I can simply say save groups, and it's going to do the same thing. So it added a second one to my spreadsheet. Actually, the average is a little different, so I must have, oh, here's one way up here that I didn't include when I drew the selection box. So you can see the frequency came out the same, but the damping is slightly different because that averaged in the damping of one additional pole. Now these values are all going to be good. I think the mode shapes are going to be good, so I'm going to delete. I don't want two of the estimates in there. I only want one. So I'm going to go up here and use another command called delete, right here, delete selected modes. So out of my curve fit spreadsheet, I want to delete the selected mode. There, it's gone. Okay. So now if I turn off the cursor, because I want to recreate the fit function for all 10 modes in my spreadsheet here. And now if I go back, I can either do it here by hitting the residues button, because this particular method here already found my residues, or I can go up here to my toolbar and it says fit function synthesis. So there's another command that's curve fitting is available to me, and bingo, you can see that it now has a red fit function that's doing a very good job of laying on top of my data. Now again, this is textbook data. Your data is never going to look this clean. So in Emiscope, the best way to curve fit is to divide and conquer, work in smaller bands. Now the stability methods don't work as well in smaller bands. You're going to get a lot of computational stuff, so you have to clean up the stability picture. We can go back and use some of those other methods, but let's go back. Let's go ahead and save these shapes. Okay, this is just reminding me that exponential window damping was removed from the modal damping estimates. An exponential window was also used along with the deconvolution when we windowed this data. So that is something that happens in curve fitting when we try to curve fit auto, cross, or ODS FRF spectra. So what it's telling us is that the damping in the spreadsheet here is actually a little bit higher than it should be. So we're going to remove the effect of the exponential window. And I'm going to say OK. And let's store those in with what we call OMA modes so we can compare them with the original modal model. Okay, here they are down here. Let me put this window down now, my curve fitting, and I'll make this one large. So here are the results that we got. In the top spreadsheet, you can see that the label, these are the frequency and damping values, damping in hertz, damping in percent, two different ways to express the damping. The label shows which measurement, which curve fitter we use to get the frequency and damping. Down here below is the mode shapes themselves, and you can see they're actually called OMA mode shapes. And their units are G's, and the method that was used to get them was the AF poly curve fitting method. And then we have a lot of amplitude and phase. So we can animate these now. I can go right back and start the animation from here. And now I'm animating. Let me rearrange some things. Okay, so here's my put my original modal model down and rearrange again. Here's my OMA mode shapes. And now I can also compare them either with the MAC values, or I can just turn on the comparison animation. So let's compare shapes, and hello. Oh, this is a sweep animation, I think is not working.
Yeah.
Signed well. Oh, we're trying to animate out of the data block instead of the shape table. Mode shapes. Okay, here we have the two shape tables. So above I have the OMA shapes, below I have the original modal model. Let me rearrange these again. And how do I know that? If I click over here into the structure window, here, let me make things a little larger. The model on the left are my OMA shapes, and on the right are my mode shapes. So you can see that up here in these two. See, the little arrow is pointing to the left. That's my OMA data, and here's my mode shape data down here. Now I can synchronize these so that they are synchronized either by their MAC values or by the frequencies. How do I do that? Because right now what I'm displaying over here is 1100. Well, we're actually synchronized because I've got the 1100 hertz OMA shape, and over here I got 1108 mode shape from my modal model. And you can see their MAC value, their modal assurance criterion, is 1, which means that the two shapes are identical. Now the values may not be the same, but the shapes are the same. In fact, the values will not be the same because one was gotten from a cross-spectra set of data, the other was gotten from FRF data. There they are now. See, as I click on a shape in the OMA, the one in the mode shape model table also changes. Why is that? Well, that's because under animation, if I go down here under compare shapes, you can see that the button closest frequency or time is turned on. The other way I can match them up under comparison is maximum MAC value. So either way is going to show me when I select a shape in one table, then I get the closest frequency in the other table. So in this case, since things are so clean, I can do it that way, or I can do it with a maximum. See, as I click through here now, it's going to change based on the MAC value. And you can see that these shapes are matching up very well, at least the low frequencies, let's go on and check them all. The picture doesn't change, the shapes don't change, and the MAC values are all 1. So again, this is a bit of an ideal case, but we started out with some known data, a set of mode shapes, modal model. We excited a MIMO model with random excitation, in this case burst random, which was ideal, and you can see that the mode shapes that we got back from the process were essentially the same answer. Now the values themselves are, as I said, are going to be quite different. If I let me just kind of put these up here. Well, let me stop the animation. Go back to draw structure. We'll put him down and we'll arrange these two windows. You can see that in order to get them to cover the screen, I have to, the last one that I touch is going to keep its shape, its size, and then the other one will fill in around it. So here's our numbers. You can see the curve fitting did a very good job. The numbers are different, frequency and damping, and then the shape values are going to be quite different because we got them, their OMA shapes versus mode shapes that were gotten by curve fitting the FRF. So let's go back here and just look at shape number 1. So you can see the numbers are quite different, the phases are different, the magnitudes are different, but when we animated them in the comparison animation, the MAC values were all 1, meaning that we recovered exactly the same shape for the 10 modes, and we also got frequency and damping values that are very comparable. Different, but almost the same. No questions. We've spent an hour together. I hope this has been useful for you. Again, I apologize for being a little bit late. Next month we will maybe do some multi-reference curve fitting. I know this is a topic that many people stumble with, and so I want to continue to show you the simple ways to use curve fitting and use the different methods so that you are successful with your data. But again, as we did here, we used some very clean data, textbook data. We excited the structure with the proper random excitation so that we got very good data. And all the curve fitters will do a good job on this type of data. And that should be your goal. Whenever you're taking OMA data, operating data, or you're using a shaker or an impact hammer, you want to do the best job you can in making those initial measurements so that the curve fitters, no matter which one you use in Emiscope, they're all going to get essentially the same answer. So I'll say so long for this month, and maybe we'll see you back here again next month or sometime soon. We'll keep doing these 1-hour monthly meetings together on the internet to teach you more about how to use Emiscope as a tool to get your job done. So long for now. Bye.